Hello everybody, we're gonna have a video recording of this lecture about 6.4 stratospheric ozone. So let's go! So we'll have all the text that I talk about on the right. You can choose which things you take note of. But the first thing we're going to say in this chapter is that here is the sun, and it provides us with lots of electromagnetic radiation. So the sunlight is electromagnetic radiation that reaches us. So this will probably remind you of chapter 6.1 and the greenhouse effect. But there's basically three main groupings of these this type of light or radiation that reaches us. So here you see the wavelength on the x-axis and the amount of light that reaches Earth of these different types of wavelengths. So we see there's a peak here of radiation around 500 nanometers. And between 400 nanometers and about 700, that's the human visible range. So we call that kind of range of radiation for visible light, and longer wavelength radiation about above 800 or so is infrared, and below 300 down to about 100 nanometers is UV light. And as you can see down here on the electromagnetic spectrum, that the shorter the wavelength, the higher the energy of the radiation. So your visible light is then considerably less energy rich compared to ultraviolet light, and X-rays even more energetic, and gamma rays the super duper energetic radiation. And this UV light then is energetic enough so that it can harm organisms. And within the UV part of the spectrum, there's basically three groups of UV light. I think I said below 300 before, but it was below 400, of course, that's UV. But there's the UVA, is the lowest energy UV light. That's 315 to 400 nanometers. It's not important for you to know the exact ranges of these, but you need to know that there's UVA, B, and C, and A is the least harmful, lowest energy, and C is the highest energy, most harmful. And luckily enough, of course, the sun provides mostly UVA, but there's also UVB and a little bit of UVC. And those could then harm organisms. Luckily, there is a little shield for this dangerous UV light, and that's the stratospheric ozone layer. So ozone is a molecule that is made of 3 oxygen atoms. So you don't need to know the chemical formula of these or anything like that, but you need to know that that ozone, the name ozone. Ozone then is found in the stratosphere. Remember that's very high up in the atmosphere, above the troposphere. So there's no climate going on here or weather patterns up here that are affecting our climate, the one we think about daily. There is a bit of tropospheric ozone that is generated in, for example, smog. We'll come to that later in chapter 8. But tropospheric ozone, that's basically dangerous for us. So ozone is a toxic molecule. Luckily, then it's mostly at the stratosphere. But most of it is then in the stratosphere. About 90% of all ozone is in the atmosphere. And so you can consider, if you want, you can consider stratospheric ozone as the good ozone, and the tropospheric ozone is the bad ozone. But this chapter is going to be focused on the stratospheric ozone. Now, so you can then consider that there's this layer then of ozone between about 20 to 40,000 kilometers up in the air. And this layer, the ozone layer, blocks then the harmful UV light. So all of UVC radiation is blocked by the ozone layer. Most of the UVB light, but very little of the UVA. But the UVA is not so dangerous, so that's okay. But you need to know that stratospheric ozone absorbs UV radiation, so that protects organisms. So what is the harm that UV light, and then specifically UVB and UVC, can cause? Well, basically all living organisms at the surface of the Earth can be harmed by UV light. Basically it can then interfere with the normal functions of DNA and proteins and so on. So it can harm cells, it can lead to mutations and so on. So basically life at the surface of the Earth is basically requires the ozone layer. And this is also the reason why we think that life didn't form at the surface of the Earth, but rather in deep oceans, because in ocean the UV light doesn't go down very far. But at the Earth, at the surface of the water, we have phytoplankton, and they are specifically or especially at risk from UV light. So this can lead them to DNA damage and basically kill phytoplankton cells. And for those that survive, it may reduce their function, so they have reduced photosynthesis. So it means that we will get lower productivity in the ocean, and that will then, of course, limit productivity at all other levels of the food chain. So basically, if the phytoplankton disappear from the oceans, then we can say goodbye to all life in the ocean, basically, right? So that's not so good, I would say. Would have planetary effects. For humans, UV light is also harmful. This individual here has an opaque lens. So basically, our lenses have proteins that block UV light, and when you get too high energetic light onto your lenses, they become cloudy. So because these proteins kind of break down, and you get it becomes murky instead of being so nicely transparent as it is. So cataracts they form naturally over your life, but if you're exposed to UVB radiation, you will, and UVC, of course, you will get these much faster. So not so great. DNA damage can also happen to us, so that can lead to skin cancer. So, and I think Australia has the highest incidence of skin cancer. And I think I've said many times before that Swedes are also pretty bad at this, but that's mainly because we go somewhere else where there is a lot of light, and then we don't protect ourselves with sunblock. You can get sunburn from UVB, and that's going to give inflammatory responses in your skin and give you blisters and so on. It's going to be quite uncomfortable. And this is a pretty dramatic image of a person that has. This guy was a truck driver, and you see that the left side of the face is way more aged than the right side, and that's because, of course, you get way more sunlight on that side of your face if you're driving around all the time. So basically, the proteins in your skin, like collagen and elastin, that gives the springiness and sponginess and suppleness of the skin, breaks down due to UV light, and you will get a wrinkle formation and sagging skin. So premature aging. So skin cancer, cataract, sunburn, and premature skin aging are the ways that UV harms humans. If you want, you can also see all these nice things on this page. This is also why it's so very, 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 very important to block this with sun cream. So please do so. Or you're gonna look like this. So ozone forms in the atmosphere due to interactions between UV light and oxygen molecules. And there's been a steady state equilibrium of the ozone concentration in the stratosphere, meaning that the concentration of ozone is basically relatively constant over time. That's because there's a balance between ozone destruction and ozone formation in the stratosphere. So when UV radiation is absorbed by an ozone molecule, that molecule breaks down into an oxygen gas molecule and a single atom of oxygen. This is not how, so these single atoms of oxygen, they're very, 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 very reactive, and they then will react with something, and usually, most often they will react with an oxygen gas molecule, and then they will form ozone again. So basically get these two processes balancing each other out. And here's a tip from the examiner. You don't need to use any chemical symbols, formula, or equations for this equilibrium, so don't bother learning the chemical equations. This shows the same thing, that there's a transformation into ozone and transformation, from ozone to oxygen and oxygen atoms, and transformation turning those into ozone once again. There is also a slow natural removal of ozone. That's because these oxygen atoms may interact in such a way with an ozone molecule to form oxygen gas molecules instead, and that's going to remove ozone from the stratosphere. This is a very slow process. However, there's also a very slow addition process, and that's when UV light hits an oxygen gas molecule, and that breaks it down into two oxygen atoms that then can interact with oxygen gas to form ozone again. So this basically is how the ozone layer was formed at the beginning, right? So photosynthesis came onto the scene about 2 billion years ago, and that started to lead to free oxygen in the atmosphere, and that then absorbed UV light, and they broke apart into these, and then they started to interact with oxygen gas molecules and form ozone. And but then this UV light also breaks down the ozone, so you get this buildup of ozone from when oxygen gas builds up. But if there's way more ozone, the breakdown increases instead, so you get this balancing out. This basically shows the same thing, so we don't have to worry about it. Let's see, we'll skip this one for now, and just look at this next top part instead. So ozone depleting substances are also abbreviated as ODS. These are substances that destroy ozone. They basically augment this natural removal of ozone from the stratosphere. And some of these will have, for example, chloride atoms on them, and the chloride atoms basically will interact with the ozone molecule and steal one oxygen atom from it and lead to oxygen gas, which is a stable thing, and then take up this oxygen atom, and then it will be able to collide with a free oxygen atom again, and basically form oxygen gas again, and then this chloride can basically leave and start interacting with a new ozone molecule. So they will be long-lived and continue to break down ozone and basically increase this ozone removal process. And they continue to be there. Oh look, they didn't even have the lowercase l there. Oh my god. Whatever. So for those of you who are biologically interested, these basically work then as enzymes breaking down ozone in the atmosphere. So they will tip this equilibrium, this steady state equilibrium, and remove ozone. Now you can see here some types of aerosol or ozone depleting substances. The main one are these chlorofluorocarbons that have fluoride in them, and these are some very important ones. So these were used as propellants, so made basically aerosol cans, spray cans, foams, and deodorants, so that you can get the chemicals that were in the deodorants to actually fly out. So due to spraying of these ones, of these types of canisters, we got these CFCs, as they're abbreviated as, to be going into the atmosphere and reaching the stratosphere. There were also used some chemicals in gas-blown plastics, or the chemicals here that were important. There's some pesticides that we've used, specifically ones that contain the methyl bromide, and they have also been working as ODSs. Flame retardants have also been found to have, some of them have found to be ODSs. And old refrigerants, so basically chemicals that you have in refrigerators to make them be cold, as well as in air conditioners. Those had also CFCs in them, and that led to ozone breaking down. So basically, I think you may have heard, if you've heard about this problem, you probably heard about the refrigerators, old refrigerators having these CFCs, and those being ozone depleting substances. So we started figuring out about these ozone depleting substances in the 60s and 70s. And we've been tracking their release and have seen then a rapid increase in the release of ozone depleting substances, peaking in the 1980s, and subsequently there's been a reduction in ozone in the atmosphere, especially at the polar regions, due to weather patterns. They accumulate, and so they become low, especially lower concentrations of ozone at the Arctic, and especially the Antarctic. So here is where we talk about ozone holes. So ozone holes aren't really holes in ozone. Like, there's no ozone, it's just that there's very low ozone concentrations. And you can see here color coding of the amount of ozone at the polar region here. The orange and red and yellow and green are the higher values, and darker blue and down to red are the lowest values. And you see that in the 80s we started seeing these holes, as you may call them, at the Antarctica. So that led us to be quite worried about the impacts this would have on ecosystems and human health. And that led to the formation of the Montreal Protocol. So we're gonna let you now watch a video about how the Montreal Protocol came about, and that goes in here. Let's see if it works. If it doesn't work here, you'll if the sound doesn't work here, you'll have to pause this and play it from the PowerPoint yourself. Okay, I noticed that you didn't have the sound for that, so I assume now that you've watched this, and then we can continue just a little bit. Oh my god. There we go. Okay, so now you saw a lot of this this protocol already. You saw the causes of it and how the scientists came together and were able to show the people at the United Nations, especially within the United Nations Environmental Program. So I'm assuming you've watched this video now. That's what I'm continuing like this. They basically got the member nations and their people got to know this information, that there's an ozone layer was depleting, the causes of this depleting due to our use of activities using ozone depleting substances, and which impacts that would have both on human health and the environment. So within the United Nations Environmental Program, or UNEP, that was basically then the platform where member countries could basically decide how to reduce these ozone depleting substances. And they then developed the legally binding Montreal Protocol that was released in or signed in 1987. And that led to member countries implementing national laws that banned many ozone-depleting substances. And in addition, many companies were quickly able to develop alternative chemicals instead of these aerosols and flame retardants and so on that did not work as ODSs. So after the Montreal Protocol was signed in 1987, basically we've seen a rapid decrease in how the use of these ozone-depleting substances from a peak here in 1980, 88 or something like that, and now we're down at very, very minimal levels. As you see, there are natural emissions of ozone-depleting substances, but those are basically the same all the time. Then the Montreal Protocol was basically signed by 24 countries, but now more and more countries have signed up, and now it's 197 countries that have done so. We continue to find new ODSs, and so basically, and we find that there's legal markets for them as well. So there has been updates and to the Montreal Protocol. The Copenhagen Amendment came into place in 1992. As you already know, we've now reduced the amount of ODSs rapidly, and UNEP hopes to end the production of all. There's one kind of replacement CFC called HCFC, which now unfortunately instead is a very potent greenhouse gas. So that's a little bit unfortunate that one of the molecules that we replaced CFCs with is instead a greenhouse gas. So that's sad, but that's how it goes. If no restrictions had been made, how many more skin cancer cases would we have gotten? So more than 300 people per million of people, and after the Montreal Protocol, that's reduced, and after the Copenhagen Amendment, that's even reduced even further. Still, this has the reduction in the ozone layer still has increased the amount of skin cancer that humanity will suffer, but that's now better than what it would have been if we had done nothing. And I think we can just get through the whole thing. There's just not much left of this chapter, so let's go. Now, due to the actions of the Montreal Protocol, we've managed to stay within the safe operating space of this little planetary boundary. So here's the planetary boundary. This is where we are. So, and the evidence for us actually staying within this boundary is that the ozone holes, they are decreasing over time. Look at that. This is not so clear, but here you see the ozone hole formation that it's increased until the 2000s, and then there's a potentially possible way to see that they're smaller now. But this graph shows it slightly better. This is the maximum ozone hole area and mean over time. You see that it peaked around 2000, and there's been a slight decreasing trend, but of course it's very spiky levels since then until recent years. And projections are that the concentrations of ozone is basically slowly recovering, and we've seen recovery already, but that's projecting to continue unless we do something weird. Now, of course, there's striking similarities here with the problems of climate change, which is very interesting. But here, of course, these were niche kind of molecules for specific markets that we used. Fossil fuels are used ubiquitously, or I think it's called, well, all over the place. So I think the comparison falters? No, wait, it's not that. Whatever. It's not easy to make a comparison due to these things, or that the comparison is limited due to fossil fuels basically being all over the place, right? But this anyways shows us that we have at least been able to make changes to society together in the face of potentially catastrophic environmental problems. So everybody feels very excited about this one. Maybe in about 80 years we'll be able to sit in a similar boat and talk about climate change. I'll be dead, but you'll be able to hopefully say something about it. I hope so. All right, that's it for 6.4. It's a very short chapter, so good job, everybody. We managed. Yeah, let's just higher level later. So, bye-bye.